Anyway, if you remember today, last time we talked about enzymatic reactions and the Michaelis-Menten model, right? So what we're going to do today is we're going to take a break from that model, and I'm going to tell you something that looks completely different, and then you'll see that it's actually quite related. And so today we're going to talk about timescale decomposition. It's a powerful technique to analyze biological systems. The idea is sometimes reactions happen at different timescales, completely different timescales. Chemical reactions can move very, very fast, but the motion of a person is much slower. So, for example, a muscle is activated by chemicals moving around and moving, binding to receptors and triggering reactions, but the motion of the muscle itself is slow, right? So there's these different things that are interacting with each other that are at completely different timescales. And in biology, because these things happen a lot, it can be used as a way to analyze a system. So let's imagine a two-dimensional case, and the same thing that I'm going to say works for more dimensions as well. This is the 2D case, but same thing in more dimensions. You have x prime equals f of xy, and y prime equals g of xy. This is so far a completely general two-dimensional dynamical system, right? It doesn't get any more general than that. You got here the rates of change over time, and they are a function of the state. But what we're going to do is we're going to multiply this by a number epsilon. And the idea is that epsilon is very small. Very small, like 0.01 or 0.001, something like that, for example. So let's think about what happens in that case. What do you think happens? This whole term becomes very small, right? Okay, so then x prime is small. Which one would you say changes faster over time then? Y prime changes faster over time, x prime changes, y changes faster over time, so y prime is large. X prime is small, so x changes slowly. The way that I can think of this system is, since we're talking about ecological models, think about a system involving a hare and a rabbit. Sorry, not rabbit, a rabbit and a turtle, okay? So there's one fast animal, like the turtle. Rabbit, turtle. I need to wake up. Can I have some of that coffee? The fast system is the rabbit, and the slow system is the turtle, okay? And there are two of them interacting with each other, okay? So the question is, how does the system behave? So the way you break this down is you first analyze the system from the point of view of the rabbit, okay? So you got the rabbit moving around very fast, and you got a turtle moving very, very slowly. So we first look at the fast time scale. By the way, we can think about, let's write this here. Y is the fast variable. And x is the slow variable. The turtle. Okay, so imagine that you're a rabbit. You move very, very fast, and you're looking at a turtle. As far as you're concerned, the turtle is moving very slowly, right? Precisely because you're so fast. You know, if a turtle looks slow to us, imagine what it looks like to a rabbit. So the fast time scale is very simple. It's basically, if you're looking at it from the point of view of the rabbit, the turtle is basically static. The turtle isn't moving anywhere. So you, as a rabbit, you're free to move around and do whatever you want, while the turtle is completely static. So in this case, assume that x is constant, and let y evolve over time. So now we have a system that looks like y prime equals g of xy, where this guy now is a constant. And therefore, this is a 1D system. Now, you already know from experience that 1D systems are much easier to study than 2D systems, right? 2D systems are easier to study than 3 and 4D systems, for sure. But 1D systems are really a piece of cake. They're really easy, right? We should not be scared of these systems anymore at all. So by reducing this to a one-dimensional system, we can do a lot of things. We can figure out the dynamics of the system over time, no problem. In general, the dynamics of the system is that it's going to converge towards some steady state, right? Now, the value of the steady state will depend on x, because remember, x is now some kind of parameter in the system. It's going to shape it's going to change the shape of this function. Moreover, there might actually be more than one steady state for some of these values of x. It doesn't matter. For any of the values of x, this system is one-dimensional, and we can analyze it. Can be analyzed using standard methods. To conclude convergence of y say to a steady state, and we're going to call this steady state, let's say h of x. And notice that it depends on x, right? Because the system depends on the constant x. So let's say that it converges globally towards the value h of x, just to make it easier. It might be that it doesn't have a unique steady state, but let's say it has a unique steady state, and we call that steady state h of x. So what it means is that depending on where the turtle is located, the rabbit is going to run very, straight away to the source of food or whatever it is that it wants to go. Okay? And it stays there. Now, the second part of the analysis is now the rabbit is happy staying there where he wants to stay, and the turtle now starts moving. Okay? So now let's change the framework and think about the world from the point of view of the turtle. So according to the turtle, the world is moving, the turtle is moving very slowly. From the point of view of the turtle, the rabbit is moving very, very, very fast, right? So fast, in fact, the turtle didn't even see the rabbit moving around. When the turtle moved, the rabbit was already gone, right? It was already where the food was or whatever. So the point is, from the slow time scale, the variable y, the fast variable, converges instantaneously to wherever it's supposed to go. So in this case, for example, that the fast variable y converges towards h of x, this analysis assumes that y is equal to h of x instantaneously, because it already converged there. It's so fast, right? So assume that convergence of y to steady state is instantaneous. That is, y is equal to h of x. Okay? And if x ever changes, then y is always going to stay equal to h of x, because y is so fast that it converges instantaneously. So then that means that we are down to a system x prime equals, if you want to write the epsilon, you can write the epsilon. You don't have to write the epsilon if you don't want. Then we write f of, what do you think? Exactly, x, hx, because remember, y converges instantaneously to h of x. And how many dimensions does this system have? One dimension, that's right. This is also a 1D system. So isn't that great? We just broke down a two-dimensional system into two one-dimensional systems. which is much better than one two-dimensional system, right? What do you think, Abdon? Is it easier, two one-dimensional systems?
Yes.
It's easier, yes. Okay. So this is right now very abstract. So let's make it more concrete. Let's talk about specific systems. And by the way, this doesn't only work in two dimensions. You can make this work in any number of dimensions. If some variables are faster than the others, you can group them into two. You can group these as the fast variables and these as the slow variables and do the same thing. Fast timescale, slow timescale, and so on and so forth. Okay, let's do an example. Example would be x prime is equal to minus epsilon times y, and y prime is x minus y to the 3. All right, so you can recognize this is a special case of that. In this case, f is just minus y, and this guy is equal to x minus y to the 3. Okay. We still have that the slow variable is x turtle, and y is the fast variable the rabbit. Okay, so let's do the fast timescale first. Can somebody remind me what the fast timescale consists of? Maybe Wilson.
The fast timescale, the x is equal to 0. It's static.
X prime.
X prime.
X prime. So x is constant, right? That's right. So fast timescale, point of view of the rabbit, turtle is static. Okay. So x is constant. And the system we have is the system y prime equals x minus y to the 3, where this guy is constant. Okay, we've dealt with such systems before. That's not a problem. Here's the phase diagram. Phase diagram of a one-dimensional system. You write here y, you write here y prime. The system looks like minus y to the 3, so that's a inverted, flipped cubic line, and it's shifted up by x. So it looks like this, where this here is x. All right. Now, let's see. Danielle? For this one-dimensional system, do you want to tell me what the dynamics is? What does this system do over time? Decreases. If you start over here, you start decrease. What happens if you start over here? You start to the right, actually, to the right. So the y-axis tells you the rate of change of y. So at here, the rate of change is positive, so y is increasing. Over here, the rate of change is negative, so y is decreasing. So the system converges towards this steady state. Now, what do you think this steady state is? Sorry? X to the 1/3, that's right. So we have to set this equal to 0 and solve for, let's see, x minus y to the 3. Remember, this guy is a constant, a given constant, and so we solve for y. That means that y to the 3 is equal to x, and y is equal to to cubic root of x. Okay? So, to summarize, fast timescale, assume x is constant, turtle is there, doesn't move at all, rabbit is free to move however it wants, and what it does is it moves very, very fast towards that steady state. Steady state is cubic root of x, so we call this our function h of x. Okay? Now let's do the slow time scale. Slow time scale. What was the slow time scale again? Let's see, Natalie.
That was when the y was constant and the x was not. And the y converged to the steady state instantaneously.
Correct. So from the point of view of the turtle, the rabbit is so fast that it converges instantaneously. Okay? So once again, we can kind of say that y is constant. It's not that y is, it's not exactly that y is constant. It's just that y converges instantaneously to steady state. Okay? So y converges instantaneously to or towards cubic root of x. So now we have the system x prime equals, and then again, we can write you can write the epsilon if you want. We're talking about the qualitative behavior. The time scale is totally different. Sure, let's write the epsilon, no problem. Epsilon times y, which is, minus epsilon times cubic root of x. Okay, what does that system look like? What does this do over time? It's a 1D system again, right? Okay, Patrick, what does it look like?
Looks like a cube system. 90 degrees.
Like a what?
A cubic function rotates 90 degrees and then inverted.
Okay. Like this?
Yeah.
Okay, so this is x x prime. See, this is the reason why I wasn't sure about writing the epsilon, because remember, epsilon is tiny, 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 right? And if we multiply this thing by epsilon, it becomes really, really flat. This is not easy to draw, right? Other than that, what I'm writing here is the qualitative behavior of the system without actually multiplying it by epsilon. But multiplying by epsilon doesn't change the dynamics. It just makes everything go slower or faster, right? This here is minus cubic root of x. So what happens with x over time? Brian?
Well, it goes straight away from 0.
Away? Say that we started over here. What would happen over time?
Oh wait, no, that goes left.
Towards. Steady state, you converge towards it. Now, depending on the biological system we're looking at, x less than 0 may or may not be relevant. If we're talking about concentrations, it doesn't make any sense to talk about negative concentrations. But in general, we might find a negative x. So let's think about what happens for negative x. If you started over here, Abdon, what happens with x if you start over here?
Converges to 0.
Converges to zero, that's right. This steady state is stable. Okay, so now we have the dynamics of both the slow time scale and the fast time scale. Let's think about what happens with the overall system. Overall system. So let's think about the null claims. What are the null claims of this system? What about the y null claim? Y null claim, y prime equal to 0, that means that y to the 3 is equal to x. So let's write this over here. Y to the 3 is equal to x. What is that? It's this, right? Now I'm drawing here the phase diagram of the whole thing, of the two-dimensional system. So y null climb means that the vectors are here horizontal or vertical? At this line. Horizontal, right? Okay, horizontal. And yeah, okay, so horizontal. Okay, now what about the x null plane? Let's do it here. X null plane? Is y is equal to 0. Y is equal to 0 looks like what? Okay, and the arrows are positive. Oh, sorry, vertical. Okay. Now, if we bother to draw the, let's evaluate it over here, for example, at the point 1, 0. Okay, at that point over there. So at the point 1, 0, we have x prime is equal to 0 and y prime equal to 1 bigger than 0. So it's pointing up. And these points are pointing down. What about these guys here? Let's evaluate it at the point, let's say 1, 1. At 1, 1, we got x prime equals minus epsilon, which is negative, and y prime equals 0. So we got arrows pointing this way, and this way arrows pointing are that way. Okay, but something that I also should incorporate into this analysis is that some of these arrows are actually much bigger than the others. Which arrows are small and which arrows are large? Small, you see, right? They're multiplied by epsilon. So these ones are tiny. That's why I'm writing them small. And the green ones are normal size, but compared with the other ones, they're actually quite large. So like this. So the system has actually very vertical looking arrows. Okay? Because the horizontal component is multiplied by epsilon, you see? The x component is multiplied by epsilon, so the vectors tend to be very vertical. Okay? So that's what the vector field looks like. And the dynamics over time would look more or less like this. Okay? Dynamics over time would look more or less like this. You start with some initial condition. Let's say we start over here. At time t equals 0. And the first thing that happens is because the vectors are very big and vertical, that you're going to converge quickly towards the steady state. That's the fast time scale. Okay? The first thing that happens is that the rabbit starts moving very fast. Turtle doesn't have any time to move, so x stays very much constant. Okay? So fast time scale is convergence towards the steady state. What steady state? The steady state cubic root of x. Okay? And then, once the rabbit is happy at its spot where the food is, the turtle starts moving, right? Following the small arrows. But remember, every time that x moves, y moves instantaneously. Every time that x moves a little bit, let's say over here, y moves and becomes equal to square root of x, cubic root of x. So you stay within this null line here. And you start moving in, like this. Does that make sense? So let me show you what happens over time. Chun, and then very slowly. Okay? If you start over here, you move very fast here, and then starts moving very slowly. Notice that you never actually reach that point. You know, it's not that you actually converge towards that point and then start moving. It's more like a smooth motion. You know, start moving very fast, and then you start moving very, very slowly down here. Make sense? All right. Okay, too much time spent on this simple example, but basically that's the idea. You break it down into two different time scales, and then you can analyze what happens over time. Do you have any questions about this example? No questions. Okay. So then I'm going to give you a more complicated example. Basically, the next more complicated example. It's called relaxation oscillations. These things are very important in neuroscience. If you look at neurons over time, they do a lot of this stuff. I'm going to give you a very simple example. X prime is equal to minus epsilon times y. Y prime equals to x minus y times y plus 1 times y minus 1. Okay? Now, what was the first time scale we studied again? Fast time scale. Is from the point of view, Patrick, from the point of view of the rabbit or the turtle?
Rabbit.
That's right. Danielle, what is the assumption in the fast time scale again? Good. X is constant. X is constant. And therefore we can write y prime equals x minus y times y plus 1 times y minus 1. This becomes a one-dimensional system that allows us to study the dynamics of y, while assuming that x is roughly constant. Now, this situation now depends on what happens with the value of x. Suppose that x is equal to 0. Let's do a phase diagram. What does this look like for x equals 0? Y minus y times y plus 1 times y minus 1. It's like a cubic, right? It's a cubic that has 3 roots, 0 plus 1 minus 1. Because of this minus sign, the normal cubic y times y plus 1 times y minus 1 would look like this. But we're multiplying it by minus. Okay? So it's the opposite. It goes down, then it goes up, and then it goes down again. Okay. Now we have more than one steady state. We have 3 steady states. Let's see. Daniel, which of these are stable and which of these are unstable?
At y0, it is unstable.
Okay. What about the other two?
The rest are stable.
Good. Awesome. So solution does like this. So these two guys are stable, these guys unstable. Do you guys agree? Awesome. That's exactly what happens. Now let's see what happens for x big, for x large. When x is just a little bit bigger or smaller, this thing is going to wiggle around a little bit, and the steady states are going to change, but they're not going to be very different. They're going to be basically still three steady states. 2 are stable, 1 of them is unstable. When x is very, very big, we have this shifted up by x. Here's x. And we have one steady state, which is stable or unstable? Stable. Okay? And same thing when x is small, so big and negative, then this thing was shifted down by x. And there's still one steady state. And it's stable or unstable? Stable. Awesome. Great. So that means that we can put this information together in a graph. Basically a graph that for every value of x is going to tell us what steady state we have and their stability. So for example, for x equal to 0, what are the possible steady states for y? 0, 1, and minus 1, right? Okay? For larger values of x, we only have one steady state, which is, say, over here. For smaller values of x, we also have one steady state, which is down here. There you go. So this is a graph of the value of the constant x versus the steady states of y. Okay? We have not talked about this, but in the case of one-dimensional system with a parameter, sometimes this is called the bifurcation graph. This is a whole topic in and of itself, and I don't want to talk about it if we don't have enough time. So let's just say, for every value of x, what are the steady states of y? This is it, right? Do you guys agree sometimes there's 3 and sometimes there's 1? Right? And you agree for large x, the steady state of y is actually positive. It's this value over here. Okay, good. So now we have a picture of what happens actually in the fast time scale. I'm gonna jump ahead a little bit and show you what happens over there. Because this can actually become, in a sense, a type of already phase diagram for the original two-dimensional system. What happens? Let's say that I start over here. Imagine that x is constant, x is not changing. We're in a one-dimensional system that converges towards one steady state over here, right? So it does this. This is for this value of x, this is what happens over time. For this value of x, this is what happens over time. For this value of x, it's more complicated because there's multiple different steady states, right? So it depends, because I'm starting over here, I converge towards this guy here. If I started over here, I would converge towards this guy over here. And same thing like this for all steady states. So this graph right here, in a sense, puts together this information, the fast time scale. Okay? What about the slow time scale? The other Brian. Brian Kwan, what is the assumption in the slow time scale again?
That it converges to steady state.
Okay. Y converges instantaneously to steady state. Okay. The problem now is that it is not a unique steady state. You see, if we started if x was over here, then y would converge towards this steady state, but it also might converge towards this steady state. So it converges to steady state, but we don't have a formula for it. Okay? We don't have a formula for that steady state. Okay, fine. But it converges to steady state. Graphically, you can see what steady state it is. So now, we let x prime equals minus epsilon times y. And remember, y is a steady state. Y is a steady state that can be computed according to this graph here. So this equation over here means that if y is positive, then x is increasing or decreasing? it's decreasing. And if y is negative, the next is increasing. And doing so very slowly, because remember it's multiplied by epsilon, right? I'm going to draw over there the overall phase diagram of this system. Okay, you see that S curve over there? That S curve is none other than the y null line of the system. Y null line. Now, I'm just going to show you what happens over time. Suppose that we started. Suppose that we started over here. This is t equals 0. The fast time scale says that y is going to converge very, very fast towards this steady state, right? Okay. Now that y has essentially converged towards a steady state, x is allowed to move much more slowly. Where does x go? Remember, if y is bigger than 0, x starts decreasing, right? Y is bigger than 0, right? So x starts decreasing very slowly. Like this. As long as y is bigger than 0, x is going to start decreasing. And as soon as x changes, y changes its value, because remember, it's converging instantaneously towards steady state. It changes its value, so it hogs, and it stays on this curve, which happens to be the y null line too. Okay? Now, what happens over here? Does it keep going down forever? Well, at some point, something's going to happen here, right? What do you think happens here? Well, remember, we're following this rule. As long as y is bigger than 0, x is going to decrease. So as long as y is bigger than 0, x is decreasing. So actually, x goes right past. X doesn't have to stop here. X keeps going down. But now that x is at this value, what are the possible steady states for y? It used to be that this was a steady state for y, but if we're down here, there's no steady state for y anymore. Exactly, it shoots down to the lower part. Because you see, for this value of x, there's only one steady state for y, and it's over here. Okay? And at this point, y is happy. It's roughly converged towards steady state. And x starts moving very, very slowly up. And then lo and behold, as long as x, let me say y, x is increasing. Because you see around this point, y is negative, right? Over here, y becomes negative. Because y becomes negative, x is going to start increasing very slowly, okay? And as long as y is negative, x is going to start increasing and continue to increase. So at some point, it's going to jump over this point, and then it's going to have to go up, because you see there's no more steady state for y in here. So this is the argument. This is fast time scale, slow, suddenly fast, then very slow, then fast, and so on and so forth. And as you can see, this thing gives us oscillations. Okay? Oscillations over time. So if I drew the dynamics of this system over time, which of course is a different graph from what we had before, we can draw, for example, y over time. So let's draw this graph over here. We started at this point. Y went very quickly up. Then it started going slowly down Then at some point it shut down. Then it started going slowly up. Then it quickly went up, slowly down, quickly down, slowly up, and so forth. So there you go. A very simple looking system has actually some very interesting dynamics. Questions? Okay. We have time for one last example, which is similar to to something that we're going to do in the future, in the next lecture. Okay, so let me just talk about it. It's going to look slightly more technical, but it's the same kind of thing. By the way, let me just say one more thing about that system over there. Suppose that, okay, so this went down slowly because these arrows are tiny, right? And this went up slowly because these arrows are tiny. Suppose we change the system a little bit and we make these arrows are still tiny, but these ones are bigger. There's no problem with that. We just change the formula a little bit. So we make these arrows bigger. And these are the only arrows that are small. So then how does this look like? Okay, these are big, these are small. So then it goes up and down fast, and then it starts moving slowly up. Okay, and then again it goes up and down fast, and then up. Something like this. Does it look like something you have already seen before? Yeah, heartbeat monitor. Heart, neurons, you name it. They all look like this. They have this funny shape, right? Like this. This is it. That's what's going on. All right. So last example. And example looks like this. S prime is equal to minus S plus lambda plus S times E. Epsilon times E prime is equal to S minus K plus S multiplied by E. Okay. This example looks different because of several reasons. First of all, the variables are not x and y. The variables are s and e. Okay? So variables are s and e. Second, the epsilon is not where we're used to having it. The epsilon used to be over here. Now it's over here. Okay? Don't be too concerned about that. We can always multiply on both sides by 1 over epsilon. So we have 1 over epsilon over here. Okay, so what that means, remember epsilon is small, right? If we have 1 over epsilon over here, that means that this variable is fast, right? This number is very, very big, and this number is normal. Okay, so once again, we have something similar to before. The slow variable is S, and the fast variable is E. Awesome. So, fast time scale. Fast time scale. What are we assuming is in the fast time scale? No, Alexandra. It's fast time scale?
That x is constant.
Right, in this case, S is constant. Slow variable. So we have now E prime equals S minus K plus S times E. I'm going to ignore the epsilon just so that we can actually draw the phase diagram of this thing. What happens with this system? It's actually very simple. This is, if you think about S as a constant, this is a straight line, right? Going down like this. So it's a single steady state. That steady state is stable. What is this value over here? Well, we set this equal to 0, and we get E is equal to S divided by K plus S, right? So this value here is that over here, is that over there. Okay, since we know where the rabbit is going, we can actually give it a name. We can call this thing, let's say, H of S. Great. What about the slow time scale? Who hasn't talked today yet? Nelson. Actually, okay, Nelson. What happens with the slow time scale?
You said x probably equal to h of s.
Okay, so in this case,
S over k plus s.
Okay, sure. Let's write this. You know, we've written this several times already. So then, okay. So now we've got the dynamics of this variable. So now we're going to study the dynamics of this variable over here. And what were you saying again?
S over k plus s.
Okay, fine. So we said E is equal to S over K plus S. And we assume that this convergence is instantaneous, right? And now we have the system S prime equals minus S plus lambda plus S times S over K plus S. And we can draw this thing. Let's see if we can make sense of this term here. This is something like S multiplied by lambda plus S divided by K plus S. I'm factoring out an S minus 1. Okay. Now, this function over here, how does this function look like? How does this function look like? This thing has an asymptote, let's say around minus k or something like that. But around yeah. So basically, the only zeros of this thing are like negative, you know, things like that. This function is not particularly interesting. It doesn't do anything particularly complicated for us, but it's multiplied by S. Oh, wait a minute. S. Okay, I'm going to have to think about it. But I want to say that the only possible dynamics is down towards 0. So I have to think about how this function looks like. But why does it look like that?
Isn't there another 0?
Yeah, when is this equal to 0?
At 0 and whenever.
At 0, yes. And
The minus k over negative.
at 0 or when this thing is equal to 1, right? Okay. And this thing is equal to 1 when lambda plus S is equal to K plus S.
K minus.
And the only way that can happen is that K is equal to lambda.
K minus.
No, it should be K plus S on the
Oh.
on the line.
Okay? But let's say that they're not equal to each other, so that can never happen. Okay? And even if they do happen, then this is always 0, so it doesn't work. Okay, so basically, I guess we are assuming that K and lambda are different from each other. So this thing is never equal to 0, and that means that this is the only steady state. And then you can look at the sign of this thing, And I'm not sure exactly what, if we're making a particular assumption here, but basically the idea is that you're converging towards 0, okay? And so when you put everything together, we're going to finish now. This is the E null plane. Okay. When we're away from the E null plane, the fast dynamics calls for convergence towards this curve, which is the curve S over K plus S. So fast timescale says we start here and we converge quickly towards this value. Okay, this is fast timescale. Okay, now we can actually, yeah, I don't like that analysis over there. I don't think that's very informative over there. But what we can do is we can do a null clan analysis. Right now we don't have time anymore, but it's easy to do. You evaluate the vector field at individual points, and you find that over here the arrows are very tiny and pointing to the left. Okay? And over here the arrows are all very big and vertical. All right? So that means that the dynamics over time looks like what? And this is now the punchline for this system, is that you first go up or down, regardless of where you are, and then you move very, very slowly along this line down to 0. Okay? This is a fast component, this is a slow component. And what that is useful for, you're going to see in the next lecture. This has to do with enzyme dynamics. Little s, of course, stands for substrate. Little e stands for enzyme. And this is the dynamics of the system. And I'm going to leave it at that, and we're going to talk more about it next time.